All right. Good morning, everyone. Congratulations to all survivors. You made it. So welcome to the third day of this event. This morning, we're going to have a very special talk. Mahmoud is going to talk about relational machine learning. So Mahmoud, he's currently a senior computer scientist at Relational AI. He's been working there since 2017. He previously had the PhD from the University of New York, Buffalo. And well, he's been doing lots of recent work that has been recognized in places like the ACM POTS conference very recently, Research Highlights Awards, and many other accolades. So kind of really looking forward to this. So don't want to take more of your time. So Mahmoud, please take it away.
Yeah. Thanks for the nice introduction and for inviting me to this amazing place. So today I want to tell you a bit about relational machine learning. And to that end, we will basically start by taking a look at a concept called relational algorithms. These are basically algorithms that operate over relational data. And then we will take a look specifically at what these algorithms look like in the context of machine learning. Now, for the purpose of developing these algorithms, we will typically need some technical tools, which we will take a look at, which we call sum product queries. We will learn a bit about these queries and how to solve them efficiently so that we can use them to develop efficient relational algorithms. And then we will take a look at a specific example of a relational algorithm, specifically the linear regression algorithm in the relational setting. We will see how far we can generalize this example, and then we will end with some open problems. So what are relational algorithms in general? Relational algorithms are algorithms that are meant to operate over relational data, structured data. And the target is basically to utilize the relational structure of the data so that we can obtain better performance, save time, and obtain better results. In the context of machine learning, better results could mean higher accuracy. And ideally, we would like the output of these algorithms to be represented relationally as well, so that potentially we can use the output as an input to another relational algorithm so that we can chain these algorithms. So let's take a look at one example. This is a typical database join query where we have three input tables. Oh, this is not how it works. Where we have three input tables R over two columns x1, x2, S over x2, x3, and T. And briefly, we can think of each table as a list of satisfying assignments to the corresponding variables. So you can think of this table as the list of satisfying assignments for the relation R, in the relation R for the columns x1, x2, and so on. And the target of the query is to list satisfying assignments to all variables that simultaneously satisfy all the input relations. Or alternatively, you can think of it as we are interested in listing triples of rows from those tables where the x2 values match between these two tables, the x3 values match. So the output of this query is like one big table like this, in this example, and this table is generally asymptotically larger than the input tables because it's like it will contain combinations of rows from input tables. Now, this is briefly what a database join query is. This is not what we are interested in solving. Instead, in our setup, our input to the problem is basically a query along with some input tables. And our target is not to compute the output of the query itself. This is what database theory is for. Our target is to compute something that depends on the query output without explicitly computing the output. And this is actually for performance considerations because the output of the query is potentially orders of magnitude larger than the input. So we want to be able to run computations on the output as if the output was available to us in a materialized form, even though we don't really have it. We are just using the input tables directly. So this is basically the main philosophy of relational algorithms. Now, what exactly does this thing that we want to compute from the output look like? It depends on the application. This could be some like a low-level form of computation, like an aggregation. In the previous example, we could be asked to compute the summation of the column y squared over all rows in the output. And a non-relational algorithm would basically compute this by explicitly computing the output of the query using a database engine and then summing y squared. But this would take quadratic time in this example, potentially higher in other examples, because simply, in the worst case, the output size itself could be up to like all combinations from R and T. Instead, in a relational algorithm, our target is to push the summation inside the query. So in this example, we could realize that we could start basically by taking the summation of y squared in the relation T alone and compute an answer for every x3. And then using this answer, we can take the summation basically of these answers and sum them up in the relation S for every x2 and so on. And if we do it like this step by step, we can solve the same problem in linear time. Now, this is an example of some low-level computation. It's just an aggregation. But now, more interestingly, we are interested in higher-level computations like running a machine learning algorithm. For example, we could be asked to train some machine learning model on the output of this query, where basically we want to learn to predict y from x1, x2, x3. And in a non-relational algorithm, the typical way to do this is to materialize the output of the query as a giant matrix, and then run a machine learning algorithm. But this is very wasteful. Instead, our target in relational machine learning is to operate directly on the input tables R, S, and T, which are generally asymptotically smaller than the output size. And we want to push the machine learning inside the query or inside the database engine. This is basically the vision. Now, in order to develop these kinds of algorithms that operate directly on input relations rather than the outputs of queries, we will need to develop some technical tools that will help us describe and develop these algorithms. These we will call them the sum product queries. It's a wide class of queries that can be used to describe some class of relational algorithms. In particular, as we will see later, we will describe our algorithms as a series of solving sum product queries. And sum product queries in general are a universal language to express many problems in many domains in databases, linear algebra, constraint satisfaction, logic, and so on. And the beauty of it is that if we have an efficient algorithm to solve SPQs, we will be able to solve the corresponding problems in different domains efficiently. And this is basically the power of mathematical abstraction. So what do these SPQs look like? This will be like a very abstract slide, but hopefully it will be the only one of this form. In order to describe a sum product query, we need a semi-ring. It's basically some domain amended with some form of addition and multiplication over this domain where we have some identity elements. And most importantly, this summation and multiplication operator must satisfy the distributive property where the product must satisfy over the summation. So this is the first thing that we need in order to describe a sum product query. Now, a sum product query, just like a database join query, is over a set of variables. We are given m subsets of variables, and associated to each subset, there is a different input function. Each function, basically, this function psi1, x1, is from the assignments of these variables, x1, into the domain of the semi-ring. Like in the database join example, these would be just input relations. This is one way to think of them in a simplified way. In addition, we are given another subset of variables. And the punchline is we want to compute this expression. This expression over here is simply a product of those input functions, where after we take the product, we take a summation over a subset of the variables so that the output of this expression is a function over the remaining variables. And this is where the name sum product query comes from. It's simply a product of functions where we take a summation over some of the variables, and the output is a function over the remaining variables. This is what we want to compute. So let's take a look at one example. In this example, we have basically 4 variables A, B, C, D, and 3 functions, psi1, psi2, psi3. We are multiplying them and taking a summation over BC. So the output is a function over AD. Now, what does this SPQ actually compute? It depends on what semi-ring we're talking about and what is the interpretation of these functions. So for example, if we take the Boolean semi-ring where this product becomes a Boolean and this summation becomes a Boolean disjunction or existential quantification, and let's say we are using these functions, psi1, psi2, psi3, to encode the edge relation of the graph, then this expression becomes the conjunction basically of 3 edges, an edge from A to B, from B to C, from C to D, and then we are basically taking an existential quantifier over BC. So basically this query will be computing for every pair of vertices AD, whether there is a path, a 3 path from A to D. Now, alternatively, if we change the semi-ring and we use the numeric sum product semi-ring, and we replace these edge relations with indicator functions that return 0 or 1, depending on whether there is an edge or not, then this same query will basically be counting for every pair of vertices AD how many 3 paths go from A to D. It's the same query, but now it's counting paths instead of detecting whether there is a path. Alternatively, if we now, let's say, replace the semi-ring with the min plus semi-ring, and now suppose that the graph is weighted, and now we are using the length of each edge as basically the functions psi1, psi2, psi3, then the same query will be computing for us shortest 3 paths. And we could even, if we use the functions psi1, psi2, psi3 to encode matrices, then the same query will compute for us the product of these 3 matrices. And this is basically the power of algebraic abstractions. So we don't really have to look at these seemingly different problems. We just look at this common expression, and we develop algorithms just for solving this common expression. And the same algorithm will actually solve each one of those problems, which are seemingly unrelated. Now, let's take a look at a bit more complicated example. In this example, suppose that we have this join, and we want to compute the minimum L1 norm among all tuples x1, x2, x3, x4 in the output of the query. So how can we encode this as an SPQ? Because it's a minimum, you might guess that we want to use something like the min plus semi-ring. And the L1 norm is also the summation, which gives us another hint. So we could start by basically trying out this expression, which is a sum product over the min plus semi-ring. But now the question is, how are we going to define these functions, psi r, psi s, psi t, such that this SPQ computes what we want? One choice is to do this, where we define the function psi r to be the summation of the absolute values of x1, x2, if the tuple x1, x2 is in R and infinity otherwise. Now, why infinity in this example? It's because it's the identity for min. So whenever a tuple x1, x2 does not belong to R, this will be infinite. Therefore, the summation will be infinite. Therefore, it will have no effect on the overall expression. And similarly, we can define psi s and psi t in this way. And now under this instantiation, this SPQ is exactly computing the minimum L1 norm among all tuples in the output. And this is generally how we can use these sum product queries to describe problems in different domains. So now that we know what SPQs look like, the next target is to learn how to solve them efficiently. And to that, we might need different ideas. The first trick that we are going to use to solve SPQs efficiently is database joins. In particular, if you consider this SPQ basically has a triangle pattern, 3 functions, xy, yz, xz. Now, if any one of those functions is 0, then the entire product is 0. Therefore, it will not really contribute anything to the summation. Therefore, we are only interested basically in tuples that give us non-zero values for these functions. Or said otherwise, we are only interested in looking at the supports of these functions. So we can take the supports of these functions, which are basically, you can think of them as database relations. And now we are interested just in the join of those relations. And only the join is necessary to compute the output of this expression. And this is how we can reduce solving this SPQ into a database join query. And there is a rich literature, actually, in database theory regarding efficient algorithms, worst-case optimal algorithms to solve this kind of queries. So for example, in this example, we know from database theory results and actually prior results in algorithms that the output size cannot exceed by output, I mean here the number of triangles. It cannot exceed n to the 3/2, where n is basically the sizes of the supports of these functions, or basically the size of the sparse representation of these functions. And we know that there is an algorithm whose runtime matches the same bound that can compute for us this expression. And this generalizes to other queries. So the main takeaway here is that the first trick that we can use to solve SPQs is basically reducing them to database joins, and then we have rich literature using worst-case optimal join algorithms, and we have also explicit bounds for every query that depend on the query pattern, and these bounds are actually tight. But this by itself is not really enough. If you take a look, let's say, at this SPQ, this SPQ is like a 3-path pattern from XY, YZ, ZT. Now, in the worst case, the join here could be quadratic in size, because in the worst case, we will have like a number of tuples XY, ZT, which are basically all combinations in psi1 and psi(x3). But this query is actually easy to solve for a different reason. In particular, if you take a look at this query and consider only the summation over t, and now if you look at these input functions, only one of them depends on t. The other two don't really involve t. And as a result, we can pull them out of the summation over t and only keep this function that depends on t inside the summation. And we can start by pre-computing this expression. Now, the output of this expression is just a function over z. And once we compute it, we are left with this query. Now, if you compare this to the original query was a query over 4 variables, x, y, z, t, and now we are left with a query over only 3 variables. We eliminated t. And eliminating t basically cost us just computing this expression, which can be computed in linear time. And this is basically what we mean by the concept of variable elimination. We can do this over and over in order to solve this query overall in linear time. In general, so this is basically the second technique that we have. The first technique was database joins to solve these SPQs. The second technique is variable elimination. In general, we actually need to combine these two techniques to solve general SPQs efficiently. If you take a look at this more complicated SPQ, here we have 5 variables, A, B, C, D, E, and 5 relations. We are taking a summation over B, C, D, E. And now, in order to solve this SPQ, we can use variable elimination, and then we have many choices to eliminate variables. For example, we can start by trying to eliminate the variable d, but this will force us basically to take a product or a join of those two relations, the w and t, the relations that contain d, in order to compute this expression. But in the worst case, this join actually will cost us a quadratic time. Alternatively, we can try eliminating another variable. If we eliminate e instead, then we only need to join those two relations. But still, in the worst case, this join is also quadratic size. Alternatively, we can notice that when we eliminate e, we can also utilize the projection of the support of this relation on CD. And now if you take a look at just this part, the part that involves CDE, now it's a triangle. And now we have seen earlier that we can solve a triangle in time n to the power of 1.5. So now using this idea, we can basically solve this query in smaller runtime, in n to the power of 1.5 overall. We just need to be smarter about which variable order to choose and how we include the projections. And then every time we want to eliminate a variable, like E, we have to use a worst-case optimal join algorithm. So this is basically the general strategy that we are going to use to solve SPQs. We have to find a good variable ordering to eliminate variables one by one. We use the projections when we eliminate a variable potentially to reduce the runtime, like the relation T prime here. And every variable elimination corresponds to solving like an SPQ using a join algorithm. And if we put all these components together, we come up with a definition called the SPQ width, which basically determines the best exponent in the runtime for solving a specific SPQ. Briefly, we have basically to take a minimum over all variable elimination orders because we can pick the best of them. Once we pick the variable elimination order, we need to consider like the worst variable elimination step because we have to do all of them one by one. So we take a max over variables. And now to eliminate every variable, there's an SPQ that captures this elimination step. And we need basically the maximum runtime exponent for solving this SPQ. So this definition is just an abstract definition that basically, for a given SPQ, it will tell us the best runtime exponent in which we can solve this SPQ. And like this definition gives us a value of 1 for acyclic queries, just like the 3-path query that we looked at earlier. And in general, it actually corresponds to some pre-existing notions of width in the database theory literature in different scenarios, which basically tells us that it's sort of like a stable or a natural notion to deal with. So the main takeaway is that now we have an algorithm to solve SPQs, which is basically variable elimination amended with the worst-case optimal joins. And moreover, now we have like a clear, basically, parameter or function to measure the runtime of a given SPQ, which is this. So this is basically the main takeaway so far. Now, before we move on to using SPQs, just a quick quiz on guessing the runtime to solve a specific SPQ, or the runtime exponent to be more specific. If you take a look, for example, at this query, this is sort of a 3-path pattern. We have a 3-path from X, Y, Y, Z, Z, W, and we are taking a summation over all variables. Now here we can start by eliminating the variables one by one. You can start by eliminating W in linear time and Z in linear time and so on. So based on this, you could probably guess that the SPQ here is 1, which means that it can be solved in linear time. The second query here is similar, except that we are taking a summation only over X and W. But still, we can eliminate each one of them in linear time, which will still lead us to an SPQ width of 1. This expression over here, you can think of it as actually sparse matrix multiplication, where we have two matrices in the sparse setting, and we are multiplying them, and we are interested in the complexity in the sparse setting, where we are measuring the complexity in terms of the number of non-zeros in those two matrices. And this cannot be solved in linear time. This gives us actually an SPQ width of 2. And finally, the query below here is basically multiplying a chain of matrices also in the sparse setting. And it is still actually, in order to multiply a chain of matrices, you can multiply 2 of them at a time. So this still has the same complexity as one matrix multiplication, except that you have to repeat it 2 times. So it's still a quadratic time. And this is basically just a quick example regarding what these like SPQ width measure or runtimes look like for different kinds of queries. And now that we have seen how to use SPQs to encode problems in different domains and how to solve them efficiently, we are now ready to take a look at how we can actually use them to develop faster relational algorithms for machine learning. So let's start by taking a look at our first and only example for a relational algorithm, which is the linear regression algorithm, the textbook linear algorithm, the textbook linear regression algorithm in the relational setting. Now, this example is based on a few papers which are a result of collaboration between Relational AI and the database group at UZH. And there are also some related lines of work coming from UC San Diego, among other places. So what does the setup of our problem look like? We are given a feature extraction query. In particular, we are given like a database query like this, where we have some input tables. In this example, we have a table, let's say, that maps a pair of item and a city into the sales of this particular item in this particular city. We have another table for item and the price. There isn't necessarily a functional dependency here. I'm assuming that as the same item could have multiple prices in different places. And then there is a table that maps city to a country. And we are basically we are given this query, which basically maps item, price, city, country into sales. So we are given some input tables, and we are given a query that computes this output. And our target is basically to learn how to predict sales based on item, price, city, country. So we are basically treating these four columns as input features, and this is basically the target that we want to learn how to predict. And we want to learn how to predict this using linear regression with square loss. However, the only trick here is that we don't want to compute the output of this query explicitly. We want to basically run linear regression directly on these input tables for performance considerations, for one thing, which is, as we mentioned before, the output of this query could potentially be asymptotically larger than these input relations. Now, the traditional textbook algorithm to solve this problem is basically structure agnostic. It doesn't really look at the relational structure of the query. Instead, to solve this in a traditional way, we just compute the output of the query in a big table, and then we will have to do one-hot encoding for categorical features. For example, item here is a categorical feature. It doesn't make sense to use it directly in the training data. We need to expand it into a 0-1 vector for different items, and so on. We have to do this for cities and countries, and we end up with this bigger table. And finally, we feed this table into some machine learning tool so that we can extract the best parameter vector theta, which has the same dimensionality as the number of features in this one-hot coded format, so that the inner product of any row in this the matrix with this training vector will be a good predictor of sales. So this is basically the target in linear regression. And typically, we want to select theta to minimize this loss function, where basically we are taking a summation over all training data pairs of the difference between the actual sales and our prediction, which is the inner product here. And there is a regularizer term. So this is what the objective function in general looks like, and we usually optimize this using batch gradient descent. This is basically the classic approach for doing this outside like the database, or without basically utilizing the relational structure of our training data. And what exactly are the shortcomings of this structure agnostic approach? First of all, we will pay a double price in basically blowing up the size of our data. Like our input data was just these tables, the S, P, and the C tables. But then if we perform the join explicitly, the output size here of the join is actually potentially asymptotically larger than the sizes of the inputs. And even worse, when we do one-hot encoding for categorical features, we will end up with something that is even bigger. So we are paying a blow-up price twice in this process. In addition, we are basically destroying the data structure that we already had. In particular, like, put yourself in the shoes of the machine learning algorithm and imagine yourself looking at this big table where you have no idea where this table came from. You might need to scan like too many rows in this table before you start inferring that every city has a unique country and so on. And if there is like some joint relationship, you might need to look at like, even as a human, you might, if you don't know where this table came from, you might need to examine too many rows in this table before you start realizing that there is some joint relationship in this table because it came from a join. But then what happened here is that we had this information up front. We knew the structure, except that we intentionally basically destroyed it from before we feed our data into the machine learning engine. just because the machine learning engine has no capability of ingesting this structure. So it's like we are paying a price twice. We spent a lot of time destroying our data structure, and now we are wasting the machine learning engine trying to relearn this structure from plain data where it has no idea where this data came from. And there is also another drawback here is the expensive move of large amounts of data between two different infrastructures, one for databases and one for machine learning. In addition, there are extra drawbacks here because these different components now treat each other as black boxes. So like, let's say after we finished training our model, let's say there is a change in some of these tables, in one of these tables. Now, in this framework, the only solution is basically to run the entire pipeline on the updated data in order to relearn from scratch. Because these components view each other as black boxes. There is no way to communicate effectively and update and propagate it through this pipeline. And this basically motivates our new approach, which is the structure-aware approach, where we want to utilize basically the relational structure. Here is one way to achieve this and still get basically the exact same output as if we were running the traditional linear regression, except that we will get it a lot more efficiently and with some extra benefits, as we will see later. So what does our approach generally look like? It basically consists of 3 steps. The first step is to factor out parts of the computation that don't depend on the model theta that we are trying to learn, that only depend on the data. And the idea here is that this vector theta that we want to learn is going to change iteratively because we are running batch gradient descent to discover a better theta every time. So it will change a lot during the training process. But these computations that do not depend on theta, we can perform them only once upfront. And then we can run, let's say, batch gradient descent, and theta will change so many times. But these computations are fixed upfront. We don't have to pay the price again. So this is basically our target, our first step. We want to factor out parts of the computation that don't really depend on theta, compute them once, and then we can deal later with finding the best theta. And now these computations, we want to encode them as sum product queries so that we can utilize the variable elimination algorithm that we have seen earlier to solve these sum product queries efficiently. This will be the second step. And finally, when we encode these computations as sum product queries and when we run variable elimination, we will naturally discover that these computations can have many duplicate sub-expressions that we can share, that we don't have to solve separately. So we don't have to solve these SPQs separately. Instead, we will keep track of common sub-expressions and reuse these results when we are solving these SPQs. And these are basically like the main major steps in our framework, where the benefit basically comes from, at least in terms of runtime. So let's take a look at each one of these steps one by one. What exactly do we mean by factoring out parts of the computation that don't depend on theta? Consider again our objective function, which is a function of theta. As I mentioned before, it's a summation over all data points of basically the difference between the predicted value minus the actual target, and then there is a square loss. I know it's too early in the morning to be examining such complicated math after a very heavy dinner last night. So please ignore this line and just look at this, which is basically just a quadratic form in terms of theta. So this is basically the main takeaway, is that our objective here is just a quadratic form in terms of theta, where we have this function, this matrix sigma, which basically controls the quadratic term, and then there is a vector c for the linear term in terms of theta. And this is basically the main takeaway here, is that if we can pre-compute this matrix sigma and this vector c, then this is basically the part of the computation that depends on the data and does not really depend on theta. We can start by pre-computing these two alone, and then we can run gradient descent only afterwards to figure out what is the best theta. So this is the first step. This is how we will break our computation down. We will start by pre-computing this matrix sigma and this vector c, and we will worry later about how to find the best theta. And same thing, the gradient here, out of this expression, the gradient will be a linear function. But it's also written in terms of the same matrix sigma, the vector c, and theta, which we will worry about later. So the first step here is just to compute sigma and c. And now our next target is to compute them, encode this computation as sum product queries. And for that, we need to take a look at the meaning of this matrix and vector. Imagine our training data in one hot-coded format. So every row here, basically these are our one hot-coded features, where again, like since item is a categorical feature, you have to do one hot encoding here. Price is a numerical feature, you can use it as it is. So these are the input features, this is the target. Now imagine this entire matrix. Again, we are not really going to actually materialize this matrix. This is just, I'm trying to explain the semantics of sigma and c. What do they actually mean? Now imagine going over this matrix row by row, and for each row we take the outer product of the row with itself. When you take the outer product of this row with itself, you get basically a square matrix like this. And now imagine we are going through every row, row by row, and doing this, taking the outer product, and we are summing up all these square matrices that we get. And now, oops, colors are not really showing up. And now basically the matrix sigma is this part of this big matrix. It's the part that I'm highlighting here. And instead the vector c is basically this vector, which is also identical to this vector. So this is basically the semantic meaning of this matrix sigma that we want to compute and the vector c that we want to compute. And now the question is how can we compute them or encode this computation as sum product queries? To that end, we will basically break the matrix sigma into blocks. One block here, let's say, is for the correlation of item with item. Like you can think of this part of the matrix as going through these rows one by one, where for every row we take the outer product of just the item part with itself. And we have similar entries. So for example, here we have an entry to analyze the correlation between item and city. You can think of this as going over this matrix and taking the outer product of the item part with the city part, and so on. So this is basically how we can break down this matrix into individual blocks. Each block is basically corresponds to correlation between two of these input features. And now the second step is to encode each one of those block matrices as the output of some product query. Let's start with item. Now this is our query, the query that gives us the training data. Now we replace the input tables by indicator functions, where these indicator functions basically return 0 or 1 depending on whether the tuple is in the corresponding relation. So for example, this indicator function over here returns 0 or 1 depending on whether this tuple is in the relation S, and so on. And now notice that the product of these indicator functions is 1 if and only if the tuple is in the output of the query, and it is 0 otherwise. So whenever we take, let's say, a summation over this product, it's exactly identical to taking a summation over tuples that are only in the output of the query. And we exclude all, we are implicitly excluding all tuples that are not in the output because thanks to these indicator functions. And now what does it mean to take the outer product of item with itself in one row of this expression? Item is a one-hot coded feature. It's just 0 or 1. So we can use it like as a group by variable in the head. You can think of the head here as a binary relation where it's basically item, comma, item. Because eventually we are computing a matrix. So you can think of the head here as like item, comma, item. It's 2 dimensions as a matrix, but only the diagonal entries of this matrix play a role, which is why we are just keeping one copy of item. So it's basically a vector, but it's an implicit representation of a matrix. And we are taking a summation over all other variables. So this is the SPQ that will compute this part of the sigma matrix. If we take a look at another part, let's say item city, Both of them are categorical features. So both of them are one hot-coded features, and the outer product is basically a matrix. So it's the exact same expression, except that we group by item and city. So city here, in the previous expression, we were taking a summation over city. Here now we are moving city to be like a group by variable in the head. And now we are computing a binary relation of item city. And this is basically the part of the sigma matrix that captures the correlation of item and city. Now, in other examples, let's say we want to take the correlation of item with the price. Price is a numerical variable. So the output here, price is just a scalar in some sense, whereas item is a vector. So the output here, when you take the outer product of a scalar with a vector, you get basically a vector. And in order to do this, the value of a price will need to participate in this product. And we only group by the categorical variable item. So this is basically the general principle, is that whenever we have a numerical variable, a numerical feature, it has to contribute, its value contributes directly to the product inside. And whenever there is a categorical feature like item, it remains as a group by variable in the head. And this is now the expression that computes this part of sigma. Similarly, if we want to take the correlation of a price with the price is a numerical feature. So the correlation of a price with itself is just one scalar. It's just a, it's just a scalar. It's a matrix of dimension 1 by 1. And to compute this, we take the square of a price in this summation and in this product, and we sum up everything. And this is how we can encode the computation of sigma, different blocks of sigma, as SPQs. And now we have already seen how to solve these SPQs using variable elimination efficiently. But something interesting will happen when we look at what variable elimination does to these SPQs. If we start with this sum product query and run variable elimination, we will end up realizing that we can start by eliminating the price column alone over just this part, and the country column alone over just this part. And then we only take a summation over the remaining features afterwards. But each one of those summations is just over one table. Now, if we dissect another part of the sigma matrix, let's say the correlation of item and city, and run variable elimination, we will end up with the exact same sub-expressions, where here we will end up just eliminating price in this table and eliminating country in this table. But these two expressions are shared among those two SPQs. Only this part will change. But now we don't have to, we can basically reuse these, the results of these sub-expressions, we can compute them only once. And this pattern is something that we will realize over and over. Once we start breaking different SPQs for different parts of sigma using variable elimination, we will start detecting many duplicate sub-expressions, and we can share the computation of these sub-expressions across different SPQs representing different parts of sigma. And this will be basically the third component in our framework, which helps us reduce the time complexity further. Yeah, so basically, these are the three main steps in our framework. First, we factor out the computation of this matrix sigma that does not depend on the layered parameter theta, so that we can compute it only once upfront. And then we update theta using batch gradient descent. And then we encode the computation of this matrix sigma as sum product queries. And while we are solving these different sum product queries, we can detect shared parts of the computation so that we can reuse them. This is in terms of runtime. But what else do we gain out of this approach, which is the relational approach for machine learning? Other benefits that we get out of the box in this approach is that database relations are natural representations for sparse tensors. In particular, just because we are encoding our computations as like database queries, we will naturally end up only computing and storing non-zero parts like of all the tensors and matrices involved. For example, in the previous example, the query that computes item sigma for item city, the correlation of item and city, will naturally only compute non-zero entries. and will only store those without us having to worry explicitly about using sparse representation or eliminating non-zeros. Similarly, in this approach, just because we are encoding our computations as SPQs, which are basically database queries, we can piggyback on the database query optimizer to solve these SPQs efficiently. Moreover, like advanced database optimizers can utilize, let's say, integrity constraints. So for example, if there is a functional dependency from city to country, then a good query optimizer will be able to simplify away a trivial summation like this. In addition, another advantage of this approach is that we will be able to piggyback on the database query evaluator. So for example, if the database engine supports where optimal joins, then we will basically match exactly the same complexity that we have seen earlier that is implied by the SPQ width. In addition, just because we are encoding our computation as a collection of database queries, most database engines support parallelization, and as a result, our machine learning algorithm will be parallelized for free out of the box. We don't have to worry about parallelization. We are just encoding our machine learning algorithm as a series of database queries, and we are leaving the rest to the database engine. Similarly, most database engines will support naturally like incremental maintenance. And this will give us basically incremental learning for free or dynamic learning for free. In particular, when some input table changes, the database engine will naturally update the computations, the outputs of the SPQs, and naturally it will update the matrix sigma. And as a result, it will also update for us the vector theta. Without us having to worry about this entire process, we just change our input data, and the pipeline, the database engine, will basically update the learned parameter. So basically, we will get incremental learning for free. And these are the main benefits we will get out of the box, just because we are encoding our computations using database queries. In addition, of course, the biggest benefit, which is the runtime saving, which is like an asymptotic runtime saving. It's not like a constant factor saving. And now the question is, how far can we generalize this simple linear regression example? How far can we push this approach? Out of the box, this approach applies to other models, for example, polynomial regression, factorization machines, principal component analysis. With some extra work, if we expand the class of SPQs to support linear inequalities, then we can cover more models. For example, piecewise linear functions, support vector machines, k-means. But unfortunately, the model that is, for some inexplicable reason, is on everyone's minds nowadays is deep neural networks. This model is not really supported by this approach. One way, like one very high-level explanation of why this is the case, you can think of it as deep neural networks. They like immediately chew the data structure. As you advance in the deep neural network, one layer after the other, the data structure gets destroyed like exponentially when you move from one layer to the next, to the point that once you reach like a deep layer in the network, you have no more any structure to analyze. And this is why this relational machine learning approach starts losing its effectiveness. And this is sort of the first obvious open problem in this line of work, which is, can we really extend these relational algorithms to work, let's say, for deep machine learning structures, in particular deep neural networks? Is there somehow some way to keep track of the relational structure even in these deep neural networks that keep chewing this structure away? This is one open problem. Another open problem is, which is probably more low-hanging fruit, can we utilize the relational data structure to design a specific model structure that is tailored to learn over this specific structure? To give you an analogy, as we saw on the first day, for data which is basically graphs, there is a specific neural network structure which is GNNs, graph neural networks. It's like a model structure that is designed to learn over this particular data structure, which is the graphs. Now, is there a similar notion here? If we have, let's say, some relational data or some factorized data, is there like a class of neural networks that is like relational or factorized in the sense that it's pre-designed to learn over this particular data structure that we have? It's not clear how we can do that in general, but this seems a reasonable direction to look at, to tailor model structures for a specific data structure, so that basically the data structure is reflected in the model structure, so that this model is potentially a lot more efficient in learning over this data. Just like, for example, GNNs are a lot more efficient and accurate when we learn over graphs than an arbitrary neural networks. Now, suppose that we cannot really do this, or suppose that we fall short in achieving this goal, tailoring a model structure. We could still talk about imposing some constraints on the model parameters so that we can rule out combinations of model parameters that don't really make sense for our training data. Like, as a simple example, suppose that our training data has some functional dependency. Now, the model itself does not really, the model could be, let's say, a neural network. The model itself does not really know about the nature of the training data. It has no idea to tell that there is a functional dependency here. But because of our knowledge that there is functional dependency in the data, we could be able to prune out some part of the model parameter space. We could impose some constraints on the model parameters saying that this combination of parameters does not really make any sense under this functional dependency. And therefore, we will save a lot of training time just because we are basically injecting this high-level information upfront into the model. This is also another possible direction. In particular, here, the main takeaway is that we could potentially use the relational data structure, utilize it in at least two different ways. We could use it to tailor our model structure for this particular relational structure, or we could at least try to use it to design some constraints on the model parameters that prune out or rule out combinations of models that don't really make sense for our relational data, instead of just relying on the algorithm to detect this, on the machine learning algorithm to detect this after so many iterations and after seeing so many data samples. These are some of the suggested future directions, and thank you so much for listening.
Thank you, Mahmoud, for that talk. And I think now we have a few minutes for questions. So, yeah, question.
Thank you, Mahmoud, for a very interesting talk. So my question is about the disappearing structure in the deep neural network.
Mm-hmm.
Do you consider the network as atomic piece of structure?
A what?
A sort of atomic piece of structure. Do you want to describe it as the entire network as one is some product query? Did you consider alternative ways to see sort of each layer as a sum product query and consider a composition of them?
Yeah, we basically can dissect the network layer by layer. Now, the first layer, in some sense, it still sees the relational structure. Like imagine in the simplest example, imagine that our training data is just a cross product or a Cartesian product of two different relations. Now, the first layer can still see this. But now the first layer is already mixing combinations of those input rows, and now it's basically applying some nonlinear function on them. Now the second layer, it will be hard to tell, if you just have the input to the second layer, even as a human, if I just give you the input to the first layer, it will be easy for you to infer that this data is just like a Cartesian product of two unrelated tables. But now, if you look at the output of the second layer, even as a human, it will be very hard to infer that there was this relationship in the data. It will be hard to reverse engineer the data structure in some sense. So this is basically roughly the intuition of why we have been struggling with this.
Okay, thank you.
Can you go back to the slide with the large sigma matrix? Yes, that one. So I was, for example, this sigma item, that's the identity matrix, right? Is it? I think it just has ones on the diagonal and zeros everywhere else.
Sigma item. Yeah, so basically here we are going over every row here. and taking the outer product of item with itself. So basically, it will be a diagonal matrix where, let's say, the entry corresponding to quote will include the count of how many rows in here have item quote.
Ah, okay, it's the count. So because I was looking at it and I was thinking, well, that's just the identity matrix. Do you really need to compute anything there? But then it's not entirely. It just seemed like maybe as a human, I would think there's maybe a slightly simpler way to construct the result than computing all those SPQs. But then maybe if they are cheap anyway, it doesn't make much of a difference.
Yeah, so like in this example, you are almost right. It's not exactly a diagonal matrix, like it's not exactly an identity matrix. It's like the counts of every item, which is simple enough. Now, in case of polynomial regression, it will get a little bit more interesting because now you want to count like different combinations of different items.
Thank you.
All right. More questions? Yes, Igor.
In the beginning, you showed us some submarines, right? But then at the end, as far as I see, it's only one submarine is involved, right? Which is like numbers. So is it, can you get anything interesting from other submarines? Okay, Boolean, maybe not Boolean, but I don't know. This mean plus, which you showed us, does it play any role?
Oh, yeah.
Or like some max, or no, max times, right? Is another one, like any other interesting submarines?
Yeah. You are absolutely right. This is actually like a good point. Some product queries in general are like interesting on their own, just as a tool to solve different problems. For this particular application, you are right that technically we only used like this submarine, which is the same as this submarine. So like the algebraic abstraction here was not really very helpful for this particular application. I just wanted to explain it along the way because it also helps us connect better basically to database engines. Because like if you here we are not really optimizing for this particular submarine. Instead, we are relying on a database engine. And in a database engine design, it's better to write your optimizer in an abstract way that does not really hard code the submarine so that you don't have to repeat this work. So yeah. In this application, yes, you are right. Yeah. Good observation, thanks. So in some sense, like this algebraic abstraction is very similar to the concept of interface in software engineering, where usually we start by writing separate algorithms for different applications until we realize that there is a unique interface that combines them, and then we combine our code. It works the same way. So it's just for the sake of database optimizers to make them more compact.
Another question?
I also wanted to ask about if you consider different kind of models. So, for example, the models that inherently have, not inherently, but have some built-in recurrence in them. Do they admit any sort of modeling as some product queries, maybe with some recursion added?
Built-in what?
So neural networks don't have any recursion in them. They are stateless functions, right?
Yeah.
So in the database world, we can handle queries with the recursion.
Oh, I see. Yeah, it's an interesting direction. What if we consider basically recursive models? I would imagine that we might start running into the same problem as deep neural networks in the sense that as you go over more iterations of recursion, the data structure also starts getting destroyed exponentially. But we haven't looked into that in detail. So, what is that?
There are generalizations of this submarine stuff to data log programs where there are recursion, right? Okay, Dan Oltiano is actually, I don't know, maybe he was not the one, but anyway. So there is naturally recursion there.
Yeah. Like basically to be a bit more specific, Like to be a bit more specific, some parts of the pipeline that I described will still be applicable, but there are certain parts that might start failing when you start considering recursion. In particular, I just want to go back to this slide. I think what will happen here is that we might end up running into trouble in this first step. These second steps will work regardless of whether we have recursion or not, because this will just be SPQs. But the first step here, this factorization, we might start running into trouble in here. But yeah, I mean, it's definitely worth reflecting upon, dissecting exactly which direction, which steps in this pipeline will struggle with different generalizations when we go into different generalizations of the problem.
Okay, maybe we have a minute for a very quick question, if anyone has it. If not, I will take advantage to ask a question. So you talk about how there is a difference between the non-relational approach and the relational one.
Mm-hmm.
And I was curious if you could give some ideas about how much speed up you gain when you have the relational approach, or like from an experimental point of view, how big is the advantage that you have when you have the relational approach?
Like, it depends on the application. There are some detailed experiments that we published in some of those papers. There can be actually like many orders of magnitude, because this is like an asymptotic speed up. It's not a constant factor speed up. So when it applies, you can indeed get like an unbounded gap, basically, where basically like the non-relation approach simply does not really terminate. But then, of course, like to be realistic, this does not cover every single machine learning models. It covers like the simplest ones where you can still see the relational structure.
All right, thank you. So please join me in thanking Mahmoud for this great talk.